All right, welcome to chapter 18, the ray model of light. And I know you're thinking, woohoo, she skipped chapter 17. And no, I didn't. We're actually going to go back to chapter 17. So light has these two models that work for different situations, different ways that we can think about light. And so we've kind of touched on EM waves, right? That is electromagnetic waves, which includes visible light. All of the things that you see are reflecting or transmitting visible light waves. And so one model for light is a wave. And while you might accept this, you're not that familiar with it because it's only specific to some really weird circumstances that you don't experience a whole lot. What you're more familiar with is the ray model of light, where light comes down out of the heaven in the form of beams, and these things make shadows, and they reflect off of mirrors. And so you are much more familiar, and you've got a lot more experience with the ray model of light. And so that's where we're going to start our study of light. We're going to learn a few laws about reflection and refraction, transmittance, and things like that before we go into this kind of more complicated and specialized model of light. And so know that the ray model is just that. It's a model. It's not perfect, but it's a really good foundation for starting to understand light. And so chapter 18 really focuses only on the ray model of light. So the ray model of light assumes 5 things, and if you're following along in your book, these are on page 575, and they've got accompanying pictures, but I'm just going to walk through these really quickly. So the ray model of light is really great because it works for a lot of your real-life observations. Like I said, you're familiar with it. It makes the following 5 assumptions. One is that light travels in straight lines, and so if I've got a bulb, then light goes from the bulb to my eye. And that's it. There's no curving. It doesn't go around corners. It only travels in straight lines. The next assumption is that light rays can cross. And so if I have one laser beam shining up and another laser beam shining down, those can cross and then continue on. They don't interact with each other in any way. They just cross and then continue on their straight-lined paths from assumption number 1. Assumption number 3 says that a ray will continue to go on even if it crosses another light ray until it interacts with matter. And so that's a solid, a liquid, or a gas, at which time it can do one of 2 things. That light ray can be reflected off of the material, it can be refracted, or it can actually experience a combination of both. It can be reflected and refracted. Once a material... it kind of depends on the material of what that light ray is going to do. So like glass and mirrors are really good at reflecting light, whereas things like prisms or plastic are not so good at reflecting it so much as they are refracting it and allowing that light to pass through in some capacity. Number 4 and 5 here are the ones you're not going to like. And so number 4 says that every object in our world is a source of light rays at every point in the object. And so you're not going to like this because you typically think of sources as only being like light bulbs or computer screens. And what this is saying is that, well, the pencil in front of you and the paper in front of you and your book and the keyboard and all of these things that don't inherently glow themselves are still a source of light rays because light rays are coming in and they're actually reflecting off of that object to give you the color that you see, right? Some of those rays are absorbed, but some are reflected too, and that's what it's allowing you to see it. And this happens at every point in the object. And then the last one is that the eye sees by focusing a bundle of light rays. And so if I have a Christmas tree, I know it's past Christmas, I know. If I have a really crooked Christmas tree and my eyeball, and this is typically how we represent an eyeball, right? The top of the Christmas tree, as well as every other point on the Christmas tree, is sending out light rays that are scattered. And some of these light rays are focused in by our eye, some of these scattered light rays. And our eye has a special lens, and we'll talk about lenses later, that kind of focuses these light rays into an image on the back of our eye that our brain then flips and interprets and says, oh, that's a Christmas tree, right? And specifically, that's the star at the top of a Christmas tree. Simultaneously, every single other point on an object that we look at is reflecting light rays, and our eyes focus those bundles of diffuse light rays. All right, so this is kind of an expansion of number 4 of the assumption of the ray model, that light comes from everywhere. And so I told you weren't going to like this, but it gets a little bit better. Light can come from one of 2 places. It can come from self-luminous objects. That would be like your cell phone, your computer screen, a light bulb, Christmas lights, the sun. Anything that produces light is a self-luminous object. Or light can come from reflective objects, which is really anything you see that doesn't make its own light, but instead reflects it. So you've probably got a light on in your room right now, and that light is shining on different things, and you see different colors. That white light has all the colors in it, and the colors that you see are the wavelengths of light that are reflected from that object back to your eye, which then does number 5, it focuses those bundles for you. All right, so sources of light rays. So self-luminous objects can be 4 different kinds. There are ray sources, point sources, extended sources, and parallel ray sources. I'm not going to grill you about this, but I do kind of want to go through them. Right? And so a ray source, a really great example, is a laser. It sends out a single beam, which actually has a lot of beams within it, but it's a pretty good approximation of just a single ray of light. There are things like a point source. These are very small, they must be very small lights, like a Christmas light. And from within the light, light kind of emanates out in every single direction from within that light to make just one little point, right? You see a dot when you see a Christmas light from far away. There are extended sources, which are like point sources, but bigger. And so this would be like a normal light bulb. And then from every single point on the light bulb, light is emanating out in these rays that travel in straight lines forever, in all directions, infinitely many directions, right? And so an extended source is just a larger source. And then there's a parallel ray source. So a parallel ray source is kind of like a ray source, right? Only, again, bigger, like a flashlight. And so when you shine a flashlight, you actually have a beam of light that goes out. And that kind of acts, it's bigger than just a ray source, but you've got lots of rays in there that kind of travel in a straight line along the foreseeable path, right? All right, so when light comes in contact with things, it can do a few things. It can reflect, it can refract, or it can be absorbed, and we're going to go into talking about all of those. And so our first one is a reflection. There's 2 kinds of reflections. There's type A and type B. Type A is a diffuse reflection, and that's what you see from most objects in your life, right? So a diffuse reflection is where you've got kind of a bumpy surface, and light comes in and it bounces off, but all of the light rays bouncing off are kind of in different and varying directions based on the rough part that they hit. And so what you get is really like a texture. And so when you look at your shirt, you're seeing reflected light rays, but you don't see a reflection. What you think of as a reflection proper is what we're going to call a specular reflection. And so this is where you have a nice smooth flat surface where those light rays are able to come in and bounce off and come in and bounce off. And there's none of this jibber jabber of a rough surface. And so a specular reflection is created by like a mirror or a spoon or a smooth pond of glass, something where these light rays don't get all scattered and confused. With this type of reflection, we see a dullness or just like a dull color, right? We don't see our light rays going in and being reflected back. With this one, we actually see what you consider and what you know as an actual reflection. Okay. So there are some things that are nice and smooth and glassy that give us these specular reflections, and then there are other things that give us diffuse reflections. I put this on first because it is by far the more common reflection in our world. There's really only a few things that give us these specular reflections. All right. I told you there's two other interactions that light can do. So with a reflection, it can go into an object and bounce off, right? Whether that's a perfect bouncing off or a scattered bouncing off doesn't matter. Reflection is just a bouncing off. And that's not a super technical term, but it gets across the idea. The other two ways that light can interact with objects and matter, so solids, liquids, and gases, is that it can become refracted or absorbed, and we're going to take a second and talk about those two. And so refraction is where light doesn't bounce off an object, it goes through it, right? And so this would be things like glass. We can get reflections from glass, but ultimately, like with windows, light does go through them, and as it goes through them, it actually bends and kind of changes direction. And this is a really great example, a good picture of a refraction of light. You've also probably seen light refraction and not really thought about it, but in terms of your windows at home, so you have the sunlight coming in from outside and it's shining on your window, but then it bends as it comes in your window and kind of just shines on one little part of the floor. It doesn't go straight through all the way. And you've probably seen that maybe on like a dusty day in the house. And so a refraction is a bending of light as it travels from one medium to another. And that's another really important part of refraction. In our ray model, one of our first assumptions is that light doesn't bend. Well, as long as it doesn't interact with any kind of matter, it doesn't bend. But as soon as that light goes from air to glass, or from air to water, or from water to air, it can go in the opposite direction too, those rays tend to change and they tend to bend. And we'll talk about that a little more in detail. But we call that bending as it goes through refraction. And then last but not least, there is absorption. So absorption happens when light neither reflects from nor goes through a material. That light energy is absorbed by whatever material it's coming in contact with. And so I love this example. We've got gummy bears. We're shining a light on them. If I just had one gummy bear, the light would actually probably refract through it. But because I have three lined up, you can kind of see that light energy being absorbed as it goes through all three of the gummy bears. By the time it gets to the third gummy bear, all of the light has been absorbed, and there is very clearly no light passing through the gummy bear. You've also probably felt light absorption when you wear dark colors in the sunshine. Light is a kind of energy. And if you have on a black shirt on a hot day, right, you tend to get really hot, as does your shirt. That is because as those light rays come in with all of their energy onto your black shirt, they don't really get reflected. That doesn't happen, right? They get absorbed, and so does all of their energy into your shirt, and so you experience heat, you experience hot. So again, as a little bit of a review, light can reflect or bounce off of objects. Or light can be absorbed and not transmitted nor reflected by the material. And when that happens, we see the color black, or we see light kind of just disappearing into a substance and not coming back out of it. And so shadows are actually a result of absorption by these rays. And so, like we said, rays travel in straight lines. And when they encounter an object that they neither reflect from nor refract through, they're absorbed by this material, and what we see is the absence of light or a shadow created by that object. All right, the law of reflection. So we're gonna go into reflection and refraction in a little bit more detail. We're gonna start with reflection. So the law of reflection says that an incoming ray and the reflected ray are both in the same plane, and they have equal angles to what we're going to call the normal. Okay, so that's a lot of information. We're going to say that we've got this mirror down here, and we have an incoming, or what we're going to call an incident ray. And so there's this ray coming in, and the normal is any line that is perpendicular to that surface. And so this normal actually makes a right angle with our mirror. And so as we have this ray coming in, we have another ray that exits, and that's called the reflected ray. And we usually draw an arrow to indicate a direction of travel on these things. And what we say is that the incident angle is equal to the reflected angle. And so that's all the law of reflection says, is that the angle of incidence is equal to the angle of reflection with regard to what we're calling the normal, or this perpendicular line coming out of that reflective surface. Right? This still abides with diffuse reflections. The only difference is we have a lot of different normals. And so diffuse reflections happen with rough surfaces like our clothes or a book. Things that we even perceive as smooth, like maybe the pen or pencil that you're holding, actually on a microscopic level have a pretty rough surface. And so these are kind of microscopic reflections. What we say though is that, like, for this substance down here, we can call this maybe the paper that you're writing on. This light ray has a normal here, right? And so it's got this dotted line that's perpendicular to that surface. Well, but then this normal is directed in another direction, and this normal is coming up this way. And so the law of reflection is still true for each one of these beams, that the incoming angle is equal to the outgoing angle. But what's different is that the normals are facing all of these different crazy directions. And so what we get is kind of this scattered or dull light in that object that we're looking into. And again, even objects maybe like your pen or your pencil or the keys on your keyboard, the paper you're writing on, they look smooth to us, but on a microscopic level, and that's definitely how we need to think about these kinds of reflections, they're very, very rough. And so this is an example of a microscopic view of paper. Right? Something you consider smooth is very rough, and so the light gets scattered in all directions, and that thing looks dull. All right. As far as the law of reflection, we're going to mostly talk about plane mirrors. Because these surfaces are so irregular, they're really hard to predict. And we don't really look at anything under a microscopic level to see how it's going to reflect, because, well, in our eyes, it doesn't reflect. It just has a color. And so we're going to consider plane mirrors. A plane mirror is just a flat mirror, like the one that you use in your bathroom, or a pocket mirror. And we're going to use the law of reflection to study kind of images in these plane mirrors. So a plane mirror is just a simple flat mirror. It has two very special qualities. One, and the first important one, is that the image formed in the mirror is the same distance as the actual object from the surface of the mirror. And so if I am looking in a tall mirror and I am 3 feet away, then my image, my image, that is the exact opposite of me, also appears to be, well, 3 feet away. And if I move closer, if I move 2 feet away, then my image appears to move closer. And that's a really important part of plane mirrors. The second part is that a virtual image is formed. And so is there actually somebody else 3 feet behind the mirror? No. It's just this projected kind of virtual image. It's not actually there, but it mimics what's exactly in front of it. It looks the same as what's in front of it, and it's upright like I'm upright. And that'll come into more play later. All right. So mirror ray tracing. When we see an object in a mirror, one of the most important things, like I said, is that the object appears in the same place, just like behind, right, the mirror. And so, like, if I have a candle over my head, well, the candle still appears over my head in the mirror, right? And what happens is we've got a point source here. Those light rays come down to the mirror, and they are reflected into my eyeball. We also know that because of the law of reflection, that this incident angle is equal to the reflected angle. Okay? And because of that, what I see, so I draw this is the incoming ray, this is the outgoing ray, and then to figure out where something is, well, okay, it's the same distance behind the mirror as the actual object. And then what I can do is take this reflected way and kind of trace it back into the mirror like this. And I can say, oh, okay, well, that's where the top of the candle is. And for plane mirrors, this is a really easy thing. It's going to be at the same height as the object that I'm looking at, and it's going to be at the same distance, like behind the mirror, as the actual object is. But because of the law of reflection, we can know that that's true. And so your book poses a really interesting question on page, on page 580. And so if you're following along in your book, and it says, okay, if I have a person of height h, what's the smallest mirror that they can see their whole self in? All right, and so what we say is, well, they've got this distance L from their eyes to the top of their head, and then they've got this distance L2 from their eyes to the bottom of their feet. And well, I know that because of the law of reflection, that this incident angle has to be equal to the reflected angle, that the mirror needs to start at least halfway up L2 in order for this component to be true, for those angles to be equal. And so, it's the same distance from their eyes to the bottom of the mirror as it is from the bottom of the mirror to the bottom of their toes. And, well, then the same is true from their eyes to their forehead. It needs to be the same distance from their forehead to the top of the mirror as it is from their forehead to the top of their eyes, right? In order for the law of reflection to be true, that the incident angle is equal to the reflected angle. And so what we find is that this mirror actually has to be 1/2 of L2 plus 1/2 of L1, right? And situated just perfectly so that they can see exactly the top of their head and exactly the bottom of their feet. If you at any point get confused about tracing rays and images in a plane mirror, please refer to this image on page 579, and it will tell you, okay, well, we've got all of these rays coming out, and I know because of the law of reflection that the incident angle is equal to the reflected angle, and oh, yeah, that's right, our eyes collect bundles of rays that get kind of focused back into our eye, and we'll talk about lenses later in the week. All right, so I'm going to move on to refraction. And refraction, remember, is when light bends as it goes from one medium to another. And so like as it goes from air to water or from water to air. Light changes speeds as it passes through these different mediums. And because of its change in speed, it kind of bends. And we'll do a really fun demonstration in class to show you kind of how that happens. But as light passes from medium 1 to medium 2, it's going to change direction. And there's a special quality about these mediums that's going to kind of determine exactly where that light goes. And so refraction occurs again because of light being transmitted through material. It bends and changes speed due to what we call the index of refraction. And that's a property of matter that you will look up, and it is represented by the variable n. And so when you start to see these n's in equations or photos, that is talking about the index of refraction, and it's like the density of a substance. It's an inherent characteristic that doesn't change. It's a constant value. We also talk about the angle of incidence, and so when we have an incoming ray, we still have a normal that's perpendicular to both surfaces. The only difference now is that it goes all the way through. It goes from one surface to another. So this still forms a right angle. And so the angle of incidence is the angle between the incoming ray and the normal. And then we also have, instead of the angle of reflection, we now have the angle of refraction. And this is the angle, again, between the ray and the normal as it is extended through that second substance. All right. The law of refraction, or for short, we call this Snell's law, is that the index of refraction of substance 1 and sine of the angle of incidence, right, and the angle of incidence, again, is this. When I multiply those two values together, they are equal to the index of refraction for the substance 2 and the angle of refraction. And again, the angle of refraction is down here. Some problems are going to try and give you the angle between like the ray and the water. Know that to do that, you're going to have to subtract from 90 to get the actual angle of incidence, angle of refraction to make this one true. And so again, I have an incoming light ray, and it bends. These angles are specifically talking about the distance between those light rays and the normal. And so this is like theta 1, and this is like theta 2. All right, and then this will be substance 1, like air. And substance 1 isn't always air, but it's where the incoming ray is from. And this has an index of refraction N1. And we can say maybe this is like water, and it has an index of refraction N2. Right? And then at that point, once you know 1, 2, maybe 3 of these values, it just becomes a plug and chug and solve. And okay, well, what is this going through? Page 582 has these common indices of refraction. And so when you go to page 582 up in the upper left there is a table. And so if you look at that table and I say, well, what is the index of refraction for water? Well, water is 1.33. So H2O is 1.33. And well, what about air? Well, air, just normal nitrogen and oxygen filled air is 1. Right? And we go on to talk about different kinds of materials like diamonds and glass and oil and all kinds of good stuff. There is this generalization that I want you to know though. So air is generally the lowest index of refraction that we'll deal with. And then everything beyond that kind of has more matter in it, you can think about it as having a higher index of refraction. And it's kind of a reflection of the density of that material. And so if light is moving from a low index of refraction to a high index of refraction, then what we see is that that light actually bends towards the normal. And so if I have this situation where light is coming in, instead of going straight, right, we've got our normal here, that light is going to bend towards the normal, make a smaller angle here than the angle of incidence. However, the reverse is true. If I have, let's say light is coming out of the water, and I've got my normal here, then when it comes from a high index of refraction to a low index of refraction, it's actually going to bend away from the normal. And so this angle is still going to be smaller than this angle. The only difference is the direction of travel. And so when we talk about this, those indexes of refraction on page 582 are going to come in real handy, as are these two generalizations. As it moves from low to high, that angle gets narrower, the light bends towards the normal. And as it moves from high to low, that light actually moves away from the normal. All right, and so one of your best friends in solving these refraction problems is going to be pictures, right? So draw out and talk about, okay, well, I know I'm dealing with air, and I'm going to label it air, and then I know I'm dealing with water, and then I'm going to go to page 582 and write out the indices of refraction. Oh, and then it's actually going to go to air again, and so I need to write that index of refraction again. I know that the angle between the water and the ray is 30 degrees, and so the angle of incidence, it should actually be 60 degrees, right? And that's the one I care about for Snell's law. And then, well, what is this angle? This angle I can predict from Snell's law, and we're going to go ahead and do that. And so Snell's law says that N1 and sine theta 1 are equal to N2 sine theta 2. Alright, so I'll go ahead and write it out. I've got the index of refraction of air is 1 times sine of 60 degrees is equal to 1.5 sine of theta 2. I want to know what theta 2 is. And so what I'll do is I'll go ahead and multiply out sine of 60 degrees is 0.86. I'm going to divide both sides by 1.5. 1.5 divided by 1.5 is going to give me, so I get 0.57 equals sine theta. And then to get theta, remember I would kind of want to divide by sine, which is actually taking the inverse sine of both sides. And so I'm going to bring my work up here and say sine to the negative 1 of 0.57 is going to equal my theta 2. And I find that theta 2 is equal to 35.2 degrees. And then I ask myself, okay, well, does that make sense? And well, yeah, it does, because it's going from a small index of refraction to a big index of refraction. This angle should be smaller than this angle, and it indeed is. And so that answer makes sense, right? We also experience an interesting thing that happens with refraction. And one of those things is, as something is going from a high index of refraction to a low index of refraction, so if I'm like a diver in the water and I'm shining a light out, there comes a point and there comes an angle where the angle between my ray and the normal is large enough such that, well, no light actually gets out. Most of it becomes internally reflected and goes back into the water. This is really interesting. We use it practically in a lot of ways. One of the places you're most familiar with seeing this is diamonds. It's what makes them sparkle. And so as light goes into a diamond and then tries to kind of bounce off a wall and get out of that diamond, at certain angles, and specifically the angles that they cut diamonds at, all of that light is internally reflected and that diamond seems to shimmer and glow. This is also the principle behind fiber optics. And so for all substances, this is going to be different. And that critical angle where all of that light is reflected inside the substance with a high index of refraction, this is called the critical angle. And all it is a plug and chug as a result of those indices of refraction. And so you just do the inverse sine of a substance 2 over substance 1. And this is only true when the index of refraction for 2 is less than 1. So when you're going from a high to a low index of refraction. So you should have a high number on top and a lower number on bottom. And that's the only way it's going to work. Right? If you've ever been in a swimming pool, this is really interesting. As you have light rays from inside the pool going out, you can see light coming in within this window. But beyond that, light doesn't really leave this window. And so after you reach that critical angle, you get this funny little underwater thing that you can only see the things directly above you. And this is actually called Snell's window, because of Snell's law. So Snell's window. And Snell's window happens because of this total internal reflection that happens. If I'm underneath this person, then I see light waves coming up. They're beyond that critical angle, and so they just get reflected right back down, and I can't see anything beyond that. I only have this little circle that I can see through called Snell's window. All right. Like I said, we use this in diamonds, and so as light comes into a diamond, diamonds are cut to create that total internal reflection, and we get this shimmer and sparkle because of it. We also use this in fiber optics, and so if you have ever had like a laparoscopic surgery, they insert this cable and they shoot a laser down at the critical angle or greater than the critical angle. It is totally internally reflected, and so they can have this kind of bendy tube that goes in and shines a light, right? And this kind of defies that whole light only travels in straight rays. Well, when we have things that are reflecting and refracting the right way, we can actually bend light in these fiber optic tubes because of TIR, total internal reflection. Refraction is also pretty interesting because it leads to some interesting images for us. You might have seen that as maybe you're in a pool and you reach down to grab something and you're not able to grab it. You actually just grab at nothing. Well, that's because of refraction, right? Or if you've ever seen a straw in a cup that looks broken, right? As these light waves are traveling, not only does this spoon appear broken. It appears much larger than it is. Like this spoon bottom does not go with that spoon top. And that's because of refraction going from a high index of refraction to a low index of refraction in our eyes. We can trace refraction images. They lead to some pretty funny things. We can trace a refracted image by knowing the index of refraction and the angles that are going to occur because of that. And so, like, if I have an object in the water, and okay, well, I know these light rays are going to travel out, and as soon as they hit that air-water interface from this high index of refraction to the low index of refraction, they're going to bend away from the normal. They're going to bend away from the normal, and I can find those angles using Snell's law. That whole n1 sine theta 1 equals n2 sine theta 2. I can find that as long as I know one of the angles. I can find that. And so I kind of trace this out, and then to find where, well, if I've got a person on the outside that is looking into the water, where are they going to see this object? All I do is take these light rays that have come out, and I trace them straight back in, as if they were never refracted at all. And if I do that, I see where this person sees that object. And so if this object is like a fish in our tank, right? That fish is actually farther back than what we see it because of this whole refraction thing. These light rays bend outward as they go into air from glass or water. And we take that and we trace it back, and that fish appears much closer to us than it actually is. We can find that distance as a simple function, and so we call S the real distance. S is the real distance of the fish. And we can find S prime, right, the image of the fish. Well, the distance of the image of the fish is equal to refractive index 2 over 1 times the actual distance. And so index of refraction 2, which just means the second surface that light hits, over the first surface, or the first kind of material that light is going through, multiplied by the actual distance of the fish. And beyond this, it's just a simple algebraic manipulation. And so, like for our smiley face, if I know n1 is greater than n2, then I know that as this goes outwards, this light is going to bend away from the normal. And so I've got light that's going out, and I've got these normals here, and another normal here, and that light is actually going to bend away from the normal. It's going to bend away from the normal. And then to find where this smiley face actually is, I take these lines and I trace them back in as if they were never refracted at all. And what I see is a smiley face that appears much closer than the smiley face actually is in the water. All right, which brings us to your homework. Your homework is on page 604. In class, we're going to be working on these problems, and then you've got 2 conceptual problems, and that's going to be it for the start of chapter 18. Make sure you have those notes filled out in class. That's going to be your participation. That shows me that you did your homework, and that's how you're going to get your credit for watching this video. All right, see you in class.